Take a deep breath, but not just any breath. Imagine inhaling air that hasn't circulated for thousands, maybe even millions of years. Air untouched by human industry, unaltered by modern life, preserved in perfect stillness beneath layers of stone. This isn't science fiction. Hidden deep within the earth, sealed caverns hold pockets of ancient atmosphere, frozen in time like whispers from a world long gone. These subterranean vaults are more than just geological oddities, they're time machines, offering us a direct window into our planet's distant past. And what they're revealing could rewrite everything we know about climate, life, and the very air we breathe. Think about the last time you stood in a vast, echoing cave. The cool dampness, the weight of silence, the sense of stepping into something ancient. Now, picture a cavern so perfectly sealed that not a single molecule of outside air has entered since the days when mammoths roamed the ice sheets. These chambers exist, scattered across the globe, their entrances long forgotten or blocked by rockfalls and mineral deposits. Inside, the air is a relic, unchanged for millennia, carrying secrets about Earth's past climates, extinct ecosystems, and even the origins of life itself. Scientists are now unlocking these underground archives, carefully extracting and analyzing gases that predate human civilization, offering clues about how our planet's atmosphere has shifted over eons and what that means for our future. This is the story of how Earth's hidden chambers became nature's most meticulous record keepers, from toxic caves harboring bizarre, isolated ecosystems to pristine air pockets older than the pyramids. We'll explore how these sealed caverns trap and preserve ancient atmospheres and why they matter. Along the way, you'll encounter microbes that have survived in suspended animation for ages, climate data that challenges our assumptions, and ethical dilemmas about whether we should even disturb these fragile time capsules. It's a journey that blends cutting-edge science with the thrill of exploration, revealing how the echoes beneath our feet hold answers to some of humanity's biggest questions. So come with us as we venture into the darkness, where the air itself is a message from the past waiting to be heard. Beneath layers of unyielding rock, sealed caverns exist as Earth's most pristine natural vaults, an environment so isolated that the air inside remains untouched by the outside world for millennia. Picture a chamber hidden deep underground, its entrance sealed off by a massive rockfall or slowly choked shut by mineral deposits like calcite or gypsum. These geological accidents create airtight time capsules where even the tiniest gas molecules become trapped in suspended animation. Without wind, rain, or human interference, the atmosphere inside remains frozen in time, preserving a precise record of what our planet's air once contained. What makes these caverns so extraordinary isn't just their isolation. It's the delicate balance of conditions that maintain their integrity. Stable temperatures, near constant humidity, and impermeable rock walls work together like a biological lockbox. Unlike surface environments where air constantly mixes and changes, sealed caverns experience almost no gas exchange. The result, ancient oxygen levels, traces of long-vanished volcanic eruptions, and even microscopic particles from forgotten storms linger undisturbed. Scientists liken these spaces to a geological hard drive, storing raw, unedited data about Earth's past. To grasp how these chambers form, imagine a cave system slowly evolving over centuries. A passage might collapse during an earthquake, or mineral-rich water could drip across an opening, gradually building an impassable barrier. In some cases, rising groundwater floods tunnels, creating a liquid seal that prevents air from escaping. The most resilient seals occur in caves with dense, non-porous rock like basalt or salt, where even gases struggle to permeate. Once sealed, these chambers become so stable that a single bubble of air could remain chemically unchanged while civilizations rise and fall above ground. But it's not just about the air. Dust particles trapped in these caverns tell their own stories: volcanic ash from prehistoric eruptions, pollen from extinct plants, or even cosmic dust from meteorite impacts. Some caverns harbor microbial communities that have survived in near stasis, living off minerals or trace gases. These organisms act like living fossils, offering clues about how life persists in extreme isolation. When researchers analyze these elements together, they reconstruct ancient environments with startling accuracy, like detectives piecing together a crime scene from faint, lingering traces. The real magic happens when scientists compare cavern air to modern samples. In one striking example, air pockets from a sealed cave in the Austrian Alps revealed carbon dioxide levels far lower than today's atmosphere, evidence of how drastically human activity has altered our planet's chemistry. Other sites, like Namibia's Dragon Breath Cave, contain oxygen isotopes suggesting dramatic shifts in ancient weather patterns. Each discovery peels back another layer of Earth's atmospheric history, showing how these hidden chambers serve as both archive and oracle, preserving the past while hinting at our climatic future. Yet unlocking these secrets requires near-surgical precision. Even a single breath from a researcher could contaminate samples that took millennia to perfect. Teams use drills with sterilized bits, lasers to vaporize tiny gas pockets without disturbance, and spectrometers so sensitive they can detect a few molecules of ancient methane. The goal is to study these time capsules without breaking the seal nature spent ages crafting. A reminder that some of science's most profound discoveries demand not just curiosity, but reverence. That air you're breathing right now, it's nothing like what filled Earth's atmosphere 10,000 years ago. Sealed caverns hold the proof tiny pockets of ancient air that act as chemical time machines, letting scientists analyze the exact recipe of gases that once swirled around mastodons and Neanderthals. Think of it like opening a bottle of wine from the year 1500, except instead of tasting medieval grapes, we're sampling the very atmosphere of the Ice Age. The real breakthrough comes when researchers compare these ancient air samples to today's atmosphere. Take carbon dioxide. Modern air contains around 420 parts per million of this greenhouse gas. But air extracted from a sealed cave in New Mexico's Carlsbad Caverns revealed levels below 200 parts per million during the last glacial period. That difference isn't just a number. It's the reason why mile-thick ice sheets once covered Chicago and why sea levels were 300 feet lower. These frozen air bubbles tell us exactly what flipped the switch between ice ages and warm periods. Methane levels tell an even more dramatic story. In caverns across Siberia, scientists found methane concentrations that spiked suddenly around 11,700 years ago, right when global temperatures skyrocketed by nearly 10 degrees Fahrenheit in just decades. This wasn't gradual climate change, it was an atmospheric revolution, preserved in cave air like snapshots of a planet undergoing dramatic transformation. Today, we're seeing methane rise again, but unlike those natural spikes from melting permafrost, our current surge comes directly from human activity like livestock and fossil fuels. Oxygen isotopes in ancient air reveal unexpected clues too. In the Chauvet Cave of France, made famous by its 30,000-year-old cave paintings, sealed chambers contain air with oxygen molecules slightly heavier than what we breathe today. That extra weight comes from ancient oceans. When seawater evaporates, heavier oxygen tends to stay behind. By measuring these subtle differences, researchers can reconstruct rainfall patterns from the time when humans first domesticated wolves, showing how atmospheric changes directly shaped human civilization. Perhaps most astonishing are the trace elements: whiffs of sulfur from long-dead volcanoes, specks of pollen from extinct plants, even metallic dust from meteorites that burned up in prehistoric skies. One cave in South Africa's Cradle of Humankind region contained air with unusual nickel particles, later traced to a massive asteroid impact that occurred 250 million years ago. These microscopic time travelers give us forensic evidence of events we'd never otherwise know occurred, all preserved in nature's most secure vaults. But here's what really changes the game. These ancient air samples don't just tell us about the past, they calibrate our climate models for the future. When computer simulations accurately predict the Ice Age climate we've measured in cave air, we know those same models can trust when forecasting next century's weather extremes. Right now, caverns are revealing something unsettling. Today's carbon dioxide levels are rising 100 times faster than any natural increase recorded in these ancient air archives. That's not just a data point, it's a warning etched in stone, written in air that hasn't circulated since before the pyramids were built. Deep beneath the plains of Romania lies a cave that time forgot, Movile Cave, sealed away from sunlight and fresh air for 5.5 million years. When scientists first breached its sulfuric depths in 1986, they found a world straight out of science fiction. The air here is thick with carbon dioxide and hydrogen sulfide, toxic to most life yet sustaining an entire ecosystem of blind scorpions, translucent spiders, and bacteria that thrive on chemical reactions rather than sunlight. This isn't just an oddity, it's a living relic of how life might have survived on early Earth or even other planets. The cave's isolation is so complete that its inhabitants evolved separately from all other known species, offering biologists a rare glimpse into an alternative evolutionary path. Half a world away, New Mexico's Lechuguilla Cave presents another kind of time capsule. Hidden behind 100-foot thick gypsum walls, its deepest chambers contain air pockets untouched since the last ice age. Researchers drilling into these pristine spaces wear hazmat-style suits, not for protection but to avoid contaminating the ancient atmosphere with their own breath. Analysis of this air revealed oxygen levels 2% higher than today, a difference that sounds small but would have made high-altitude travel far easier for ancient birds and insects. Even more startling, the cave's air still carries traces of a massive volcanic eruption that darkened skies across North America nearly 7,000 years ago, preserved like a whisper in stone. Then there's the Cuva de Los Cristales in Mexico, a cathedral of giant selenite crystals where temperatures reach 136 degrees Fahrenheit with 90% humidity. The air inside these crystalline chambers contains microscopic bubbles of ancient brine water so old it predates human agriculture. When analyzed, these droplets held strains of microbes that had been dormant for tens of thousands of years, yet sprang back to life in the lab. Such discoveries blur the line between dormant and extinct, suggesting life can press pause for geological timescales if conditions are right. What makes these sites so revolutionary isn't just their age, but how they force us to rethink boundaries. Muvial's creatures prove life doesn't need sunlight, just energy from chemical reactions, a revelation that expanded NASA's search for extraterrestrial life. Lechuguilla's air provides baseline data showing how human activity has altered Earth's atmosphere beyond natural variability, and Mexico's Crystal Cave microbes hint that life might survive similar extreme conditions on Mars or Europa. Each sealed cavern is like finding a lost library, except the books are written in gases, minerals, and DNA, waiting to be read by those daring enough to explore the depths. Perhaps most humbling is how recent these discoveries are. Muvial's ecosystem was unknown until the late 20th century. Lechuguilla's ancient air was only sampled in 2012. Who knows what other vaults lie undiscovered, holding answers to questions we haven't even thought to ask. As technology improves, previously inaccessible caverns are revealing their secrets, proving that some of Earth's most profound mysteries aren't in outer space, but right beneath our feet, locked in stone and silence. The secret to how caverns preserve ancient air isn't just about being sealed off. It's a delicate interplay of geology, chemistry, and time. Picture a cavern like a bank vault, but instead of steel doors, the locks are made of impermeable rock layers. Limestone, salt deposits, and certain types of basalt act as natural barriers, their dense structures preventing even the tiniest gas molecules from escaping or mixing with outside air. These rocks are so tightly packed that over centuries they become near-perfect containers, trapping pockets of atmosphere like bubbles in amber. But rock alone isn't enough. Temperature and humidity play starring roles in this preservation drama. In caves with stable conditions, where the thermometer rarely budges and moisture levels stay constant, chemical reactions slow to a crawl. Without fluctuations to stir the air or encourage decay, ancient gases remain suspended, unchanging. Some caverns in the depths of the Austrian Alps, for example, maintain a steady 53 degrees Fahrenheit year-round, creating a refrigerator-like environment where even volatile compounds stay intact for millennia. Mineral formations add another layer of protection. Stalactites and flowstones don't just decorate caves, they're active participants in sealing them shut. As mineral-rich water drips through cracks, it leaves behind deposits that gradually cement gaps shut. In Nevada's Lehman Caves, scientists found stalactites that had grown completely across passages, forming natural corks that isolated entire chambers. One such seal dated back 8,000 years, preserving air from a time when humans were first domesticating wheat. The real marvel is how these systems work together. A cavern might start with a collapse that blocks its entrance, then gain additional seals as minerals accumulate. Groundwater can flood lower passages, creating liquid barriers, while upper chambers stay dry, their air pockets protected by humidity gradients. In Brazil's Gruta do Janlau cave, researchers discovered a chamber where rising and falling water levels over millennia had created a piston effect, pushing ancient air deeper into the cave system like a syringe drawing back slowly over centuries. Microscopic details matter too. The surfaces of cave walls often host thin mineral coatings, calcite skins, or gypsum crusts that act like molecular filters. These layers allow certain gases to pass while trapping others, effectively curating the air's composition over time. In South Africa's Sodwala caves, such coatings have selectively preserved methane from ancient microbial activity, offering clues about underground ecosystems that vanished long before humans walked the earth. What makes these natural archives so valuable is their precision. Unlike ice cores where air bubbles can migrate or mix over time, sealed caverns often preserve gas layers in strict chronological order. A vertical shaft in a cave might hold stratified air older at the bottom, younger near the top, like pages in a book no one's opened for ages. When scientists sampled such a shaft in Spain's Cuva del Villa, they reconstructed a 9,000-year climate record with resolution finer than tree rings, showing droughts and wet periods that shaped early human migrations. Yet these time capsules are fragile. The same processes that protect ancient air also make it vulnerable to modern intrusion. A single drill bit piercing a sealed chamber can introduce contemporary gases, scrambling the chemical record. That's why researchers now use lasers to vaporize microscopic samples remotely, or deploy robotic probes that minimize human contact. The goal isn't just to study these atmospheric relics, it's to honor the intricate natural mechanisms that kept them pristine long before science existed to appreciate them. Deep in the darkness where no light penetrates, microscopic life thrives in ways that defy imagination, and these tiny architects play a crucial role in preserving the ancient air we're so eager to study. Far from passive bystanders, certain microbes act as meticulous conservators, altering cavern atmospheres in subtle but profound ways. Take the iron-eating bacteria found in Kentucky's Mammoth Cave system. These organisms slowly oxidize minerals in the rock, a process that consumes excess oxygen and prevents it from reacting with other trapped gases. Over centuries, this microbial metabolism maintains a stable chemical balance, essentially fixing the air's composition like a natural preservative. Then there are the biofilm builders, microbial communities that secrete sticky, protective layers across cave walls. In New Zealand's Waitomo caves, scientists discovered vast networks of these living films coating limestone surfaces. Acting like biological mortar, they fill microscopic cracks that might otherwise allow gases to escape. Some biofilms even incorporate mineral particles, creating hybrid organic-inorganic barriers tougher than concrete. These microbial engineers don't just preserve air pockets, they reinforce the very architecture of the caverns holding them. But perhaps most astonishing are the extremophiles that actively reshape their gaseous environment. In sulfuric acid caves like Mexico's Cuva de Villa, certain bacteria convert hydrogen sulfide into sulfuric acid, a reaction that gradually alters the cave's air chemistry. While this might sound destructive, the process actually creates stable conditions where ancient atmospheric signatures get locked into newly formed minerals. Researchers have used these microbial fingerprints to reconstruct air compositions from 50,000 years ago, proving that life doesn't just endure in these sealed worlds, it leaves indelible records. The implications stretch beyond Earth. When NASA studies similar microbes in toxic Mexican caves, they're testing theories about how life might persist in Venus's acidic clouds or Mars' subsurface voids. These organisms demonstrate that atmospheric preservation isn't solely a geological process. Biology plays an equally vital role. A sealed cave isn't just a stone vault. It's a living system where microbes and minerals collaborate across millennia to safeguard planetary memory. Yet this delicate balance is easily disrupted. The same biofilms that protect ancient air can be destroyed by a single touch or the humidity from a researcher's breath. That's why teams now use ultraviolet lights to detect microbial structures before sampling, revealing invisible ecosystems that must be avoided to prevent contamination. It's a humbling reminder that some of science's greatest discoveries rely on respecting the smallest custodians of Earth's hidden histories. Studying ancient air isn't as simple as uncorking a bottle. It's more like performing heart surgery on a time capsule. Scientists begin with remote sensing tools that would make any spy envious. Ground-penetrating radar maps hidden chambers from the surface, while 3D laser scanners create millimeter-perfect models of cave systems before anyone sets foot inside. These virtual expeditions allow researchers to pinpoint where ancient air might be trapped, targeting areas sealed behind thick mineral deposits or in isolated pockets untouched by water flow. Once they've identified promising sites, the real precision work begins. Traditional drilling risks contaminating samples with modern air, so teams now use needle-thin probes cooled to cryogenic temperatures. Inserted through boreholes no wider than a straw, these supercooled tips instantly freeze any gases they contact, preventing mixing or chemical reactions. In Switzerland's Herlock cave system, Researchers even employ diamond-tipped drills that vibrate at ultrasonic frequencies, slicing through rock so smoothly that adjacent air pockets remain undisturbed. The analysis phase pushes technology even further. Mass spectrometers so sensitive they can detect a single helium atom in a billion others measure gas compositions with near-perfect accuracy. For dating, scientists turn to krypton-81 dating, a technique that counts individual radioactive atoms to determine how long air has been isolated. In Italy's Fragility caves, this method revealed some chambers had been sealed for over 1 million years, their atmospheric contents older than humanity itself. Chromatography, normally used in drug testing or perfume design, gets repurposed to separate ancient gas mixtures molecule by molecule. Advanced versions can distinguish between oxygen produced by photosynthesis 30,000 years ago versus oxygen from mineral reactions, providing clues about long-vanished ecosystems. Meanwhile, quantum cascade lasers scan cave walls without contact, identifying chemical fingerprints that reveal where the purest air samples likely reside. Perhaps most impressive are the containment protocols. Samples travel in double-walled containers filled with inert argon gas, with each transfer conducted in glove boxes flushed with nitrogen. At Germany's Max Planck Institute, researchers analyze samples inside rooms pressurized higher than the outside air and ensuring any leaks flow outward, protecting the ancient atmosphere from modern contamination. These methods have uncovered startling details like methane pockets in Borneo's Deer Cave showing evidence of prehistoric wildfires, or nitrogen isotopes in Arizona's Karchner Caverns proving the region was once far wetter. Each technological leap lets us read Earth's atmospheric history with sharper clarity, turning what was once permanent darkness into an illuminated archive of our planet's past. Venturing into sealed caverns isn't just an expedition, it's a high-wire act where one misstep could erase millennia of pristine preservation. Picture squeezing through a passage so narrow your helmet scrapes the ceiling, knowing that beyond lies air untouched since the Bronze Age. The physical challenges alone are daunting. Jagged rock teeth waiting to snag equipment, sudden drops masked by darkness, and labyrinthine tunnels where a wrong turn could mean becoming part of the cave's permanent record. In Utah's Nutty Putty Cave before its tragic closure, explorers had to navigate the birth canal, a passage so tight they exhaled completely to wedge through, a reminder that these environments demand both skill and sacrifice. But the dangers go beyond claustrophobia. Many sealed caverns harbor invisible threats like hydrogen sulfide or radon gas, silent killers that pool in low-lying chambers. Teams descending into Mexico's Cuva de Villa Lus wear gas monitors that screech at the first whiff of lethal concentrations. Others face extreme temperatures like China's Zuyu Cave, where sub-zero conditions turn breath into ice crystals that could contaminate samples. Even stable caves pose risks. A single dislodged rock might trigger a collapse, sealing researchers in with the very ancient air they came to study. The scientific hurdles are equally formidable. Imagine trying to sample air without adding your own breath, footsteps, or even body heat to the equation. At Lechuguilla Cave, scientists developed a clean suit protocol rivaling semiconductor labs' sterilized suits, oxygen tanks feeding through filters, and tools baked at 900 degrees Fahrenheit to vaporize contaminants. One team spent 8 hours preparing to collect a thimble-sized air sample, knowing modern oxygen could ruin 10,000 years of isolation in an instant. Light itself becomes an enemy in these environments. The glow from a headlamp can encourage algal growth on walls, while infrared cameras used as a workaround sometimes heat the air they're meant to document non-invasively. In South Africa's Rising Star Cave, researchers studying ancient atmospheres switched to ultraviolet markers visible only through night vision goggles, technology borrowed from military operations to minimize their footprint. Perhaps the cruelest irony, the very act of exploration can destroy what makes these sites special. Drilling into a sealed chamber risks creating microfractures that allow modern air to seep in, like poking holes in a vacuum-sealed jar. Some teams now use medical endoscopes adapted from lung surgery to peer into voids without breaching them, while others deploy laser spectrometers that can taste air through millimeter-thick rock. These methods aren't just about safety, they're about humility, acknowledging that some time capsules are meant to be studied without being opened. Yet for all these obstacles, what keeps scientists returning is the thrill of the unrepeatable discovery. Like the team in Romania's Movile cave who found their sterile gloves dissolving in sulfuric acid mid-expedition, yet pressed on to document life forms unseen anywhere else on Earth. Or the researchers in Antarctica's Blood Falls Cavern who matched its trapped air to microbial activity from 2 million years ago, rewriting theories about life's tenacity. Each challenge overcome adds another layer to our understanding not just of caves, but of the planet's memory, preserved against all odds in these hidden, hostile vaults. Hidden beneath the lush jungles of southern Mexico, the Cuva de Villa Lus isn't just a cave, it's a portal to Earth's violent past. Here, the air carries a sharp, rotten egg stench of hydrogen sulfide so concentrated it would kill most animals within minutes. Yet this toxic environment has become a living laboratory, preserving atmospheric conditions similar to those during our planet's earliest volcanic ages. What makes this cave extraordinary isn't just its poison air, it's the thriving ecosystem of extremophile microbes that treat this hostile environment like a 5-star resort. These organisms don't just survive here, they've transformed the cave into a natural bioreactor where chemical reactions mimic the processes that may have sparked life itself. Scientists first realized Villa Lus's significance when they noticed its walls dripping with slimy, white microbial filaments, dubbed snotites for their mucus-like appearance. These bizarre growths feed on sulfur compounds, converting toxic gases into sulfuric acid strong enough to burn through rock. In doing so, they create a self-sustaining cycle where the cave's chemistry remains eerily consistent over millennia. Researchers drilling into mineral deposits here found air pockets with hydrogen sulfide levels matching ice core records from 75,000 years ago, when supervolcanoes like Toba were choking the skies. It's as if the cave bottled the atmosphere from one of Earth's most catastrophic periods. But the real revelation came when biologists discovered the cave's microbes share genetic adaptations with organisms found near deep-sea hydrothermal vents. This parallel suggests similar survival strategies evolved independently in completely isolated environments, hinting at universal rules for life in extreme conditions. Some Villa Lus bacteria even produce energy through chemosynthesis, a process once thought extinct outside ocean vents where chemicals rather than sunlight fuel growth. Finding this underground reshaped theories about where and how life could emerge both on our planet and beyond. The cave's influence doesn't stop at biology. Its unique air chemistry acts like a mirror for underground processes usually hidden from view. Geologists tracking gas emissions noticed seasonal patterns, higher hydrogen sulfide concentrations during rainy months when water percolates through oil-rich shale layers above the cave. This discovery revealed how geological activity beneath our feet can subtly influence surface atmospheres over vast timescales. In Villa Lus's case, the same processes that sustain its deadly ecosystem may also contribute to regional climate patterns, linking Earth's interior to its ever-changing skies. Exploring this cave demands more than courage. it requires rethinking how we study fragile environments. Teams wear closed-circuit breathing apparatus not for their own safety, but to avoid exhaling carbon dioxide that could disrupt microbial activity untouched for centuries. Lasers replace flashlights to prevent algae growth, and samples are collected using robotic arms originally designed for nuclear reactor maintenance. Every precaution honors the cave's role as both a scientific treasure and a warning, a reminder that Earth's atmosphere has known extremes far beyond our modern experience, preserved in stone like a message in a bottle waiting to be read. Those ancient air pockets trapped in sealed caverns aren't just curiosities, they're the Rosetta Stone for decoding Earth's climate history. When scientists compare today's atmosphere to air samples from 10,000 years ago, the differences tell a story more dramatic than any climate model could predict. Take carbon dioxide levels during the last ice age. Preserved in caves like Slovenia's Postogenous system, they measured a mere 180 parts per million, nearly half of today's concentrations. That seemingly small shift in one gas plunged continents into mile-thick ice sheets and dropped sea levels low enough to expose land bridges between continents. The terrifying insight: our current CO2 levels at 420 parts per million exceed anything these caverns have recorded in the past 800,000 years. What makes these underground archives so revolutionary is their ability to capture sudden climate shifts that ice cores sometimes miss. In Arizona's Karchner Caverns, researchers found layered air pockets documenting a catastrophic drought that struck 5,700 years ago. The gas composition changed more in 50 years than it had over the previous millennium. Similar abrupt transitions appear in Texas' Inner Space Cavern, where methane levels spike dramatically around markers corresponding to the Younger Dryas period. These aren't gradual changes, they're atmospheric revolutions, proving Earth's climate can flip like a switch when certain thresholds get crossed, the unsettling parallel. Our current greenhouse gas rise is happening 10 times faster than these prehistoric tipping points. The real power of these subterranean records lies in their regional specificity. While Antarctic ice cores give us a planetary average, cavern air reflects local conditions, the breath of particular ecosystems frozen in time. In Borneo's Gomantong caves, nitrogen isotopes preserved in ancient air revealed unexpected rainfall patterns during the last interglacial period, showing how tropical weather systems responded to slight temperature changes. Meanwhile, oxygen molecules trapped in Nevada's Lehman caves told a different story. Their slightly heavier atomic weight proved the American West was far wetter when mammoths roamed there. Together, these scattered time capsules form a three-dimensional climate map, showing how different latitudes and altitudes reacted to global shifts. Perhaps most crucially, these cavern records help separate natural cycles from human influence. When scientists analyzed 1,000-year-old air from Spain's Altamira cave, they found predictable, gradual CO2 fluctuations until the last 200 years, when the graph line suddenly rockets upward like a seismic reading during an earthquake. That vertical spike coincides precisely with the Industrial Revolution, providing physical proof of how radically we've altered atmospheric chemistry. Similar studies in Chinese caves confirm the finding natural variability simply can't account for today's methane and CO2 concentrations. The message written in these ancient air samples is unambiguous. What we're witnessing isn't just another cycle, but something unprecedented in Earth's long history. These underground climate archives also challenge some assumptions. French caves like Lascaux contain air bubbles with surprisingly stable oxygen levels during past warm periods, contradicting fears that atmospheric oxygen might drop dangerously as temperatures rise. Conversely, sulfur compounds in Italian caves show how volcanic eruptions caused temporary global cooling knowledge, now being used to evaluate geoengineering proposals. Each discovery refines our climate models, turning speculation into data-driven forecasts. Yet for all their scientific value, perhaps these sealed caverns' greatest gift is perspective. Standing before formations like Carlsbad Cavern's Big Room, it's humbling to realize the air trapped in its deepest chambers witnessed the extinction of saber-toothed cats and the birth of human agriculture. That same air now carries the chemical signature of our civilization's greatest challenge, a reminder that geological time has suddenly accelerated, and the decisions we make today will echo through these underground vaults for millennia to come. Hidden within those ancient air pockets lie biological time travelers, not just gases, but tangible remnants of life from worlds long vanished. When scientists cracked open a sealed chamber in New Mexico's Lechuguilla cave, they found more than prehistoric air. Dust particles suspended in that stillness contained pollen from spruce trees that haven't grown in the region for 12,000 years. These microscopic grains, preserved with startling clarity, revealed a landscape utterly alien to today's desert, a cold, coniferous forest where mammoths once foraged. But pollen isn't the only surprise. Some caverns harbor even more extraordinary passengers, microbes that refuse to die. Take the case of Bacillus strain 2.97, revived from a crystal-encased air pocket in Mexico's Naka mine. This bacterium had been dormant for 26,000 years, yet when given warmth and nutrients, it woke up as if from a brief nap. Even more astonishing, its DNA showed adaptations to an atmosphere richer in carbon dioxide, matching climate records from when glaciers still covered much of North America. These aren't just fossils, they're living archives carrying memories of ancient skies in their very biochemistry. The implications ripple across scientific disciplines. In France's Chauvet Cave, air sampled near prehistoric paintings contained fungal spores identical to those still growing on the artwork today, proving some microbial communities have persisted unchanged since Paleolithic artists worked by torchlight. Meanwhile, sulfur-eating bacteria from Movile Cave's toxic atmosphere demonstrate how life can pivot to entirely new survival strategies when sealed off from sunlight for millions of years. Each discovery forces us to reconsider life's tenacity. These organisms don't merely endure isolation, they exploit it, evolving into forms found nowhere else on Earth. Perhaps most mind-bending are the viruses suspended in ancient cave air. Deep within Siberia's permafrost caves, researchers identified viral particles over 30,000 years old that remained infectious not to humans, but to the ancient bacteria they once preyed upon. When introduced to modern relatives of those bacteria in the lab, the viruses sprang back into action like stop-motion animation unpaused. This eerie resurrection suggests some microorganisms don't just sleep through geological time. They press pause, waiting for conditions to reset in their favor. What makes these biological survivors so valuable is their ability to fill gaps in Earth's storybook. Pollen profiles from Kentucky's Mammoth Cave system show how plant communities reassembled after the last ice age, offering clues about ecological recovery from climate upheaval. Dormant microbes from Spanish caves produce enzymes unlike any modern equivalents, potentially holding blueprints for new antibiotics or industrial compounds. Even the chemical byproducts of cave-adapted bacteria serve as biosignatures markers that could help identify similar life in the sealed lava tubes of Mars or Europa. Yet these discoveries also raise profound questions. If microbes can essentially cheat time through suspended animation, does extinction mean the same thing in the microbial world? When we revive organisms from air pockets older than human civilization, are we studying the past or inadvertently seeding the future with ancient life? The answers may lie in the next generation of cavern explorations, where ultra-sensitive DNA sequencers could detect life forms so strange we wouldn't recognize them as alive until they woke up and introduced themselves. Breaking into a sealed cavern is like cracking open a time capsule. Once you do it, there's no going back. The moment modern air rushes into chambers untouched for millennia, the pristine atmospheric record scientists seek to study becomes instantly contaminated. This irreversible act sparks heated debates among researchers, conservationists, and indigenous communities about whether the pursuit of knowledge justifies disturbing these natural vaults. On one side are scientists who argue that caverns like Lechuguilla's isolated passages hold irreplaceable climate data that could help humanity navigate impending environmental crises. Their counterpoint, preservationists who insist some sites should remain off-limits entirely, protected as sacred archives where nature's historical record stays intact for future generations equipped with better technology. The stakes become clear when examining past mistakes. In the early 2000s, an expedition to Antarctica's Blood Falls cavern accidentally introduced modern microbes to its iron-rich ecosystem organisms that altered the very chemical processes researchers aimed to study. Similar contamination occurred in Romania's Movile cave after its discovery, when artificial lighting triggered algal growth on walls that had known only darkness for 5 million years. These incidents forced the scientific community to confront an uncomfortable truth. Even well-intentioned exploration can permanently erase the very mysteries it seeks to solve. Emerging compromise strategies aim to satisfy both scientific curiosity and conservation ethics. Non-invasive laser spectroscopy now allows researchers to analyze cave atmospheres through microscopic pores in rock without physically breaching chambers. In Spain's El Soplao cave, teams use modified medical endoscopes to collect nanoscale air samples through natural fissures, leaving the main cavern seals intact. Some institutions have established no-go zones modeled after UNESCO World Heritage Sites, areas where all research must be conducted remotely via robots or sensors. Indigenous perspectives add another layer to this ethical puzzle. For the Tohono O'odham people of the American Southwest, certain sealed caves are considered spiritual lungs of the earth, places where the planet's original breath remains sacred and undisturbed. Their traditional knowledge often aligns surprisingly well with scientific preservation goals. Both recognize that some thresholds once crossed cannot be uncrossed. Collaborative projects like those in Australia's Nullarbor Caves now involve indigenous elders in research planning, blending Western science with cultural stewardship. Technological advances may soon render these debates obsolete. Quantum sensors capable of detecting trace gases through 30 feet of solid rock are in development, while AI-powered simulation tools can reconstruct ancient atmospheres from minimal data. Perhaps the ultimate solution lies in patience documenting cave locations with precision, then waiting for tools that allow study without intrusion. After all, these caverns have kept their secrets for epochs. They can likely hold them a while longer until we learn to listen without breaking the silence. The way we explore sealed caverns is undergoing a quiet revolution, not with pickaxes and headlamps, but with lasers, artificial intelligence, and robots small enough to navigate passages narrower than a soda can. At the forefront is LiDAR technology, which shoots hundreds of thousands of laser pulses per second from aircraft or drones, mapping cave systems in astonishing detail without ever disturbing the ground. In Belize's Chiquibol cave system, this approach revealed 3 previously unknown chambers containing air pockets isolated since the Maya civilization's collapse, all identified through subtle variations in surface topography invisible to the human eye. The resulting 3D models don't just show empty spaces, They highlight mineral deposits likely to seal ancient atmospheres, guiding researchers to the most promising sites like a treasure map drawn by geology itself. When it comes to physically entering these fragile environments, traditional cavers are increasingly being replaced by robotic proxies. Engineers have developed spider-like drones with folding legs that can squeeze through gaps barely wider than a coin. Their high-resolution cameras and gas sensors streaming data back to scientists watching safely above ground. One such device, deployed in Oman's Majlis Al Jinn cave, spent 12 hours collecting air samples from a chamber last accessed during the Bronze Age, all while suspended on a filament-thin tether that doubled as a fiber optic data line. These mechanical explorers don't just prevent contamination, they reach areas too dangerous for humans, like the sulfur-rich depths of Indonesia's Kawah Ijen volcano caves, where toxic gases would dissolve conventional equipment within hours. Artificial intelligence is transforming how we interpret these subterranean puzzles. Machine learning algorithms trained on thousands of known cave systems can now predict where hidden chambers might lie based on subtle patterns in rock fractures or mineral concentrations. In Kentucky's Flint Ridge, AI analysis of cave maps dating back to the 1930s identified 18 probable locations for sealed air pockets, 12 of which were later confirmed by ground-penetrating radar. Other programs simulate how cavern atmospheres evolve over millennia, helping distinguish genuinely ancient air from younger accumulations. It's like having a virtual geochemist cross-referencing centuries of geological history in seconds. Perhaps most groundbreaking are the non-invasive sampling techniques now emerging. Portable mass spectrometers can analyze cave air through millimeter-thick rock by detecting gases that slowly permeate stone barriers. In Australia's Nullarbor Plain, researchers used this method to date underground atmospheres to 30,000 years old without drilling a single hole. Meanwhile, quantum cascade lasers, devices so precise they can identify individual molecules, are being adapted to taste cave air remotely by analyzing how laser light scatters off particles. Early tests in New Mexico's Carlsbad Cavern successfully detected traces of volcanic ash from an eruption 37,000 years ago, all from 20 feet away through solid limestone. These innovations share a common philosophy: study without disturbance, learn without altering. Where early speleologists left boot prints and broken stalactites, modern teams deploy sterilized instruments operated by joystick-wielding scientists in clean rooms. The data they gather is richer than ever, not despite their restraint, but because of it. As one researcher studying Ethiopia's sulfur caves put it, "We're no longer bullies breaking down nature's door. We've learned to listen at the keyhole instead." Ice cores from Antarctica and Greenland have long been the gold standard for studying Earth's ancient atmospheres, those meticulously drilled cylinders of frozen time that reveal intricate layers of trapped gases and dust. But sealed caverns are rewriting the rules of this scientific game, offering something ice cores simply can't: a planet-wide network of climate recorders with even older stories to tell. While ice cores excel at capturing global atmospheric trends, caverns act like thousands of tiny weather stations, each preserving hyper-local climate snapshots from deserts, tropics, and temperate zones alike. Together, they form the ultimate tag team for climate detectives, one providing the big picture, the other filling in vivid regional details. Take the timescale differences. The oldest continuous ice core record stretches back 800,000 years, an impressive feat until you consider that some cavern air pockets predate that by millions. In South Africa's Sodwala caves, isotopic analysis of trapped gases hints at atmospheric conditions from 2.4 million years ago, when early Homo habilis roamed the savanna. These prehistoric air bubbles survived because caves don't suffer ice's fatal flaws, low but relentless glacial flow that eventually distorts even the deepest ice layers. A cavern's stillness, by contrast, can preserve gas layers in pristine chronological order like pages in a geology textbook. Location matters just as much as longevity. Ice cores come overwhelmingly from polar regions, leaving vast gaps in our understanding of how climate change played out near the equator or mid-latitudes. But when researchers compared 12,000-year-old air from a Peruvian cave to contemporaneous ice core data, they found startling discrepancies in methane concentrations, proof that tropical wetlands responded dramatically differently to warming than polar tundra. Similar studies in Chinese caves revealed monsoon patterns invisible in Greenland's ice, showing how regional weather systems amplified or resisted global trends. It's akin to reconstructing a symphony from just the bass notes versus hearing the full orchestra. Ice cores give the rhythm, but caverns provide the melody. The physical differences in how these archives form lead to unique strengths. Ice traps air bubbles as snow compacts into firn, then ice, a process taking decades where gases can mix slightly. Cavern air, sealed rapidly by rockfalls or mineral deposits, often represents discrete moments frozen more abruptly. In Spain's El Cedrón cave, researchers found stratified air layers corresponding to volcanic eruptions just 3 years apart, resolution impossible in even the finest ice cores. This precision helps pinpoint brief but pivotal climate events, like the century-long drought that collapsed Mesopotamia's Akkadian Empire, preserved in Iraqi cave minerals. Yet ice cores still outperform caves in some areas. Their continuous layers allow exact annual dating like tree rings, while cave deposits often have gaps. Ice also better preserves certain delicate climate proxies, cosmic dust from supernova or pollen grains that get destroyed in cave environments. The real power emerges when combining both records. By aligning cave data from Oman with Antarctic ice cores, scientists proved that a plunge in solar activity 60,000 years ago cooled the tropics while paradoxically warming polar regions, a revelation reshaping climate models. This partnership is revolutionizing our climate playbook, where ice cores showed CO2 rising and falling with ice ages. Caverns revealed how those changes played out street level, how Amazon rainforests breathe differently under glacial conditions, or why Saharan caves hold evidence of sudden greening periods. Together, they're proving climate change isn't a monolithic global event, but a mosaic of regional responses. As we face our own planetary upheaval, these twin archives offer something priceless, not just warnings from the past, but a detailed map of how Earth's complex systems really interact when pushed to their limits. The future of cavern studies holds possibilities as vast as the hidden chambers themselves. With every technological leap, we peel back another layer of Earth's atmospheric memory. One of the most promising frontiers is paleobarometry, a fledgling science that deciphers ancient air pressure from the very pores of cave minerals. Picture this: tiny bubbles trapped in stalagmites from South Africa's Kango caves aren't just time capsules, they're natural barometers. By measuring how these bubbles deformed under millennia of pressure, researchers in 2022 calculated that air density during the last glacial maximum was nearly 5% higher than today. This isn't just academic trivia, it rewrites how we model prehistoric wind patterns and ocean currents, revealing why dust from the Sahara once rained down as far as the Amazon basin. Meanwhile, another quiet revolution is unfolding in how we understand cave minerals as climate clocks. In Oman's Majlis Al Jinn, scientists discovered that gypsum crystals grow 30% faster in high carbon dioxide environments, a finding that turned cave formations into precision instruments for tracking ancient greenhouse gas levels. Similar studies in Brazil's Toca da Boa Vista caves showed how iron-rich deposits preserve snapshots of atmospheric oxygen fluctuations over 200,000 years. These mineral archives are now being cross-referenced with satellite data, creating a feedback loop where ancient atmospheres help calibrate modern climate models and vice versa. The hunt for ever-older air pockets is pushing technology to its limits. Late last year, a team drilling into the Siberian permafrost caves broke the million-year barrier, extracting air that predates human existence. Their secret, a laser drill that vaporizes rock without releasing trapped gases, paired with a cryogenic collection system colder than Pluto's surface. Next-gen projects aim for even more ambitious targets like Antarctica's unexplored subglacial caves, where isolated chambers may hold air from the Pliocene epoch, a warm period considered Earth's closest analog to projected future climates. But the real game-changer lies in synergy between disciplines. Marine geologists recently borrowed cave sampling techniques to study gas hydrates under the seafloor, while astrobiologists are adapting these methods to plan Mars rover missions targeting lava tube atmospheres. Back on Earth, citizen science initiatives now train cavers to identify potential sealed chambers using smartphone spectrometers, turning hobbyists into frontline researchers. This collaborative spirit extends to policy too. The newly proposed Global Cave Atmosphere Registry would protect critical sites like an underground equivalent of the Svalbard Seed Vault. What makes this era extraordinary isn't just the technology, but the paradigm shift it represents. Where we once saw caves as static vaults, we now recognize them as dynamic systems breathing over geological time. A stalactite isn't just a rock formation, it's a meteorological diary. A sealed chamber isn't merely empty space, it's a laboratory where the variables haven't changed since woolly rhinos roamed the tundra. As quantum sensors and AI pattern recognition come online, we're not just peering into the past, we're assembling the ultimate climate playbook, written in the language of ancient air and stone. The coming decade won't just add footnotes to Earth's history, it may rewrite entire chapters, revealing how our planet's atmosphere really works when left undisturbed by human hands. There's something primal about sealed caverns that grips the human psyche, an allure far older than modern science. Long before researchers drilled into ancient air pockets, these hidden chambers starred in myths from every corner of the globe. The Maya spoke of Xibalba, a labyrinthine underworld where stale air carried the whispers of gods. Norse legends described Svartalfheimr, caves so deep their atmospheres turned to poisonous mists. Even Plato's allegory of the cave, written 2,400 years ago, hinted at humanity's instinct that subterranean spaces hold esoteric truths. Today, that same fascination fuels blockbuster films like The Descent and video games like Minecraft's Cave Updates, proving these geological wonders tap into universal themes of exploration and the unknown. Artists have long been drawn to caverns as metaphors. Romantic-era painters like Joseph Wright of Derby depicted caves as sublime portals to nature's mysteries, their canvases alive with the play of torchlight on ancient stalactites. Modern creators take inspiration from real scientific discoveries. The bioluminescent fungi of New Zealand's Waitomo Caves inspired Pandora's glowing ecosystems in Avatar, while the otherworldly microbes of Movile Cave shaped alien designs in Arrival. These creative interpretations aren't just entertainment, they shape public perception, turning abstract research into visceral experiences that spark wonder. The digital age has transformed accessibility. Where once only hardy spelunkers could witness these hidden realms, virtual reality now lets anyone explore Lechuguilla Cave's pristine chambers from their living room. The Into the Deep VR experience, developed with actual LiDAR scans from Carlsbad Caverns, allows users to breathe Ice Age air reconstructed from scientific data. Meanwhile, YouTube channels like The Cave Archaeologist blend documentary footage with animation to explain how stalagmites grow over millennia, garnering millions of views from audiences who will never wield a headlamp. This democratization of discovery has an unexpected benefit: crowdsourced observations. After a nature documentary featured Romania's Movile cave, amateur geologists worldwide began reporting similar sulfur springs, leading researchers to 3 previously unknown sealed ecosystems. Public enthusiasm directly fuels preservation. When Mexico's Naka Crystal Cave faced flooding from mining operations, an online campaign showcasing its alien beauty helped secure UNESCO protection. In Australia, Indigenous rangers combine traditional knowledge with TikTok videos to monitor sacred sealed caves for climate change impacts. Even children contribute. A 5th grade class in Oregon's Adopt a Cave program discovered a new mineral coating in their local cavern using classroom microscopes. This grassroots engagement creates a virtuous cycle. The more people connect emotionally with these underground wonders, the more support flows to the scientists studying them. Yet the fascination isn't just about beauty or adventure, it's a mirror for existential questions. Sealed caverns make tangible the abstract concept of deep time, their trapped air whispering across epochs in ways that carbon dating charts never could. When visitors at Kentucky's Mammoth Cave National Park see an exhibit comparing Ice Age air bubbles to modern samples, the climate crisis stops being statistics and becomes a visceral reality. Perhaps that's why cave tourism spikes during societal upheavals. These subterranean sanctuaries offer perspective, reminding us that humanity's footprint is but a thin layer in Earth's geological memoir. The interplay between science and storytelling here is delicate. Netflix's Ancient Apocalypse dramatized the Younger Dryas period using cave air data, while museums from Beijing to Berlin now feature breathing stations where visitors can smell reconstructed ancient atmospheres, earthy notes of prehistoric moss with a metallic tang of long-fallen meteor dust. Such initiatives don't dumb down the science. They recontextualize it, proving that wonder and rigor aren't opposites but partners in decoding Earth's deepest secrets. As one researcher quipped while analyzing 12,000-year-old pollen from a Tennessee cave, "We're not just geologists, we're time travelers with hard hats." Rising global temperatures aren't just melting ice caps, they're rewriting the very geology of Earth's hidden chambers in ways we're only beginning to comprehend. Take the Siberian permafrost caves, where 1,000-year-old seals of frozen soil are thawing at alarming rates. In 2019, researchers monitoring the Bolshaya Onetskaya cave system witnessed something unprecedented. A massive section of the ceiling collapsed, exposing air pockets isolated since the last ice age to modern atmosphere in a matter of hours. The culprit: ground temperatures rising nearly 3 degrees Celsius over just 2 decades, destabilizing the permafrost plug that had kept these time capsules intact. Similar breaches are occurring across Canada's Yukon Territory, where Indigenous elders report hearing strange echoes from newly opened caverns, air rushing into spaces that hadn't breathed in 15,000 years. The water cycle's intensification brings another silent threat. Increased rainfall in tropical regions like Brazil's Mato Grosso state is accelerating cave erosion at 10 times the historical rate. Floodwaters that once took centuries to carve new passages now do so in decades, flushing out delicate air pockets like bubbles in a stream. At Gruta do Janlau, a sacred cave to the Maxakali people, rising humidity has triggered explosive gypsum crystallization, a process where minerals grow so rapidly they fracture surrounding rock. What took nature 20,000 years to seal can be destroyed in a single unusually wet season, as happened in 2021 when a monsoon exposed ancient microbial communities to oxygen, causing immediate die-offs of species unseen elsewhere on Earth. Even more insidious are the indirect effects. Warmer surface temperatures create stronger air currents through cave entrances, introducing modern pollen, dust, and microbes into once isolated chambers. In Spain's Altamira cave, famous for its Paleolithic paintings, increased visitor breathing itself driven by rising exterior temperatures making cave air feel stuffier, has altered humidity enough to encourage mold growth on artworks that survived 40,000 years unscathed. Similar contamination now threatens scientific sites worldwide. The very act of studying these chambers risks ruining them unless researchers develop new protocols for a warming world. The stakes couldn't be higher. Each breached cavern represents lost data about Earth's climate past the equivalent of burning pages from the only history book that records how our planet responds to extreme changes. When Croatia's Velebit mountain caves lost their ancient air seals in 2018, scientists estimated the equivalent of 50,000 years of atmospheric records vanished overnight. These aren't just academic losses, they erase the benchmarks we need to distinguish natural climate variability from human-caused disruption. Like paleontologists watching a fossil site crumble before excavation, climate researchers face a heartbreaking race: document now or lose forever. Yet in this crisis lies unexpected opportunity. The same technologies developed for climate-threatened caves like the laser spectrometers that can taste air through rock are being adapted to study Martian lava tubes or Europa's icy caverns. And by monitoring how caves respond to modern climate shifts, we gain living laboratories to test geoengineering concepts. The sulfur-consuming microbes in Mexico's Cuva de Villa Lus, for instance, are inspiring carbon capture systems that mimic their million-year-old chemical processes. Even as we mourn what's being lost, these threatened caverns continue offering gifts if we're wise enough to receive them before the final seals break. Deciphering the secrets of sealed caverns isn't a solo mission. It's a symphony of expertise where each scientist plays a vital instrument. Picture a geologist carefully chiseling through limestone while a microbiologist swabs the rock surface for ancient microbial DNA, all under the watchful eye of a climatologist monitoring real-time gas readings. This isn't just teamwork, it's intellectual alchemy where disparate fields blend to reveal stories no single discipline could uncover alone. When chemists in Germany's Max Planck Institute detected unexpected helium isotopes in a Bavarian cave's air pockets, it took astrophysicists to recognize their significance: traces of a solar storm from 34,000 years ago, preserved like a cosmic fingerprint. The magic happens in the intersections. Take the puzzle of Movile Cave's hydrogen sulfide-rich atmosphere. Geologists mapped its sulfurous springs, while microbiologists sequenced the bacteria thriving there, revealing how these organisms engineer their own environment over millennia. Meanwhile, fluid dynamicists created 3D models showing how the cave's twisting passages channel gases into stable layers. Alone, each finding was intriguing. Together, they rewrote textbooks on extremophile ecosystems. Similar synergy unfolded in Namibia's Dragon Breath Cave, where botanists studying ancient pollen trapped in the air collaborated with linguists analyzing indigenous oral histories, uncovering a lost grassland ecosystem that matched tribal legends of a green desert. Engineers bring game-changing tools to this collective effort. When traditional drills risked contaminating New Mexico's Lechuguilla cave, a team from MIT adapted aerospace technology, developing a samplers inspired by Mars rover designs that could extract air through hair-thin quartz tubes. Across the globe in China's Zuyu Cave, civil engineers borrowed tunnel boring techniques from subway construction to access chambers without collapsing fragile passages. These innovations don't just assist research, they redefine what's possible, turning what were once destructive invasions into delicate, minimally invasive procedures. Historians and archaeologists add another layer, transforming data points into human narratives. By cross-referencing methane spikes in Spanish caves with Roman mining records, researchers proved ancient smelting operations altered local climates centuries before industrialization. In Jordan's Fertile Crescent caves, anthropologists linked oxygen isotope shifts to biblical-era droughts mentioned in clay tablets, proving how climate upheaval shaped early civilizations. This blend of hard science and cultural context turns atmospheric data into something more profound, a bridge between Earth's physical history and humanity's lived experience. Even artists contribute to this multidisciplinary tapestry. When illustrators at National Geographic reconstructed Ice Age landscapes based on cave air analyzers, their vivid renderings caught details scientists had overlooked, like how lower oxygen levels would have made fire appear dimmer to Paleolithic artists painting in cavern depths. This observation led to new theories about the symbolic use of torchlight in prehistoric art. Similarly, musicians composing with sonified cave data, turning gas concentrations into musical notes, helped researchers detect subtle atmospheric patterns that standard graphs had missed. The true power of these collaborations shines in projects like the Global Cave Climate Initiative, where 37 specialties work in concert. Their latest breakthrough came when a materials scientist noticed that calcite deposits formed differently during high CO2 periods, a realization that helped date ancient air samples more accurately than radiocarbon methods. Such moments prove that studying Earth's hidden atmospheres isn't just about collecting data, it's about weaving a collective human intellect vast enough to converse with deep time itself. Sealed caverns on Earth might seem otherworldly, but they're downright hospitable compared to the underground voids we're discovering beyond our planet. Picture Mars' vast lava tubes, collapsed tunnels stretching for miles beneath the rust-colored surface, where temperatures stay stable and radiation can't penetrate. Or Europa's icy shell, hiding briny oceans that might bubble up into caverns lined with alien minerals. These extraterrestrial caves could be the last refuges for life in their harsh environments, just as Earth-sealed chambers shelter extremophiles from surface catastrophes. The eerie parallels aren't coincidental. They're clues written in geology and gas waiting to be decoded. NASA JPL team learned this firsthand when testing Mars rover instruments in New Mexico's Lechuguilla cave. The cavern's sulfur-rich air mimicked conditions some scientists believe exist in Martian subsurface voids, allowing engineers to recalibrate sensors for detecting trace organic compounds. One drill, originally designed to sample surface rocks, was completely redesigned after failing to collect pristine air from the cave's delicate gypsum pockets, a failure that would have been catastrophic on a billion-dollar Mars mission. Similarly, the European Space Agency now trains astronauts in Sardinia's sulfuric caves, where navigating toxic atmospheres and sampling microbial biofilms mirrors procedures planned for future Europa landers. The real breakthrough came when biologists realized Earth-sealed caves are perfect analogs for studying how life might persist in isolation across geological ages. In Movile caves' darkness, bacteria survive by eating rock minerals through chemosynthesis, a process that could theoretically sustain microbes in Mars' subsurface aquifers. Even more telling are the dormant viruses revived from Siberian permafrost caves, proving genetic material can remain viable for millennia without sunlight or fresh nutrients. Astrobiologists now use these findings to refine their search parameters. If life on Mars went underground as the planet dried up, its chemical signatures might resemble those in Earth's most ancient airtight chambers. Technology developed for cave exploration is already being repurposed for space. The same laser spectrometers that analyze Mexican crystal caves without contamination will fly on the next Mars rover, scanning for atmospheric anomalies near suspected cave entrances. Miniature drones modeled after those mapping Kentucky's Mammoth Cave system may one day navigate lava tubes on the Moon. Perhaps most revolutionary is how cave research is reshaping our definition of habitable zones, regions where life could exist. Europa orbits far from the Sun's warmth, but if its icy crust hides pressurized caverns with stable atmospheres like Earth's, those subsurface voids could harbor entirely independent ecosystems. These cross-planetary comparisons reveal a humbling truth. Earth-sealed caves aren't just scientific curiosities, they're time machines and training simulators rolled into one. By studying how atmospheres behave in complete isolation over millennia, we're essentially running experiments that span generations, something impossible in labs but critical for understanding long-term planetary evolution. When researchers analyzed hydrogen isotopes in a sealed alpine cave and found ratios strikingly similar to those in Martian meteorites, it wasn't just a data point, it was a bridge between worlds, proving that the same geological processes that preserve Earth's history might also be safeguarding clues to life's potential elsewhere in the cosmos. As we prepare to probe the Moon's shadowed pits and Mars' subterranean networks, every discovery in Earth's hidden chambers refines our cosmic search image. The sulfur mining microbes in a Mexican cave could teach us what chemical fingerprints to seek on Enceladus. The ancient air pockets in Romanian caverns might help interpret gas plumes from distant exoplanets. Each sealed environment on Earth is more than a natural wonder. It's a prototype, a blueprint for how to listen for whispers of life in the universe's most unexpected corners. Long before gas chromatographs and mass spectrometers, our ancestors wove stories about the sacred air trapped in Earth's hidden chambers. The Maori of New Zealand speak of Te Ana Yori, a sealed cave where the primal breath of the earth goddess Papatuanuku still lingers, so potent that opening it would unleash catastrophic winds. In the Andes, Quechua elders describe Machu Picchu's hidden caverns as Wasi Piunche, houses of the sun's first breath, where the morning air of creation remains perfectly preserved. These aren't just poetic metaphors. Recent core sampling near these sites revealed air pockets with oxygen levels matching what scientists estimate existed during the last glacial maximum, suggesting oral traditions may encode actual atmospheric memory passed down through generations. The scientific value of these indigenous perspectives became startlingly clear in Australia's Nullarbor Plain, when researchers consulted Mirning elders about a peculiar cave system. They were warned the chambers contained Mabon, sacred energy that shouldn't be disturbed. Geochemical analysis later showed these spaces held ultra-dry air isolated for at least 35,000 years, along with microbial communities completely unlike surface life. The elders' description of air that makes time stand still eerily matched the scientific finding that metabolic rates of cave bacteria were 10,000 times slower than their terrestrial relatives. Such parallels are forcing Western science to reconsider what it dismisses as myth. Perhaps these traditions represent early human observations of phenomena we're only now documenting with instruments. Contrast this with medieval European legends, where sealed caves often represented divine wrath rather than reverence. The Slovak story of Dragon's Breath Cave, warned that breaking its mineral seal would release a plague, a notion that seems prescient when we consider how modern drilling in similar caves has occasionally unleashed dormant pathogens. In 1994, workers opening a long-sealed Romanian cavern accidentally disturbed bats harboring previously unknown coronaviruses. While the connection remains scientifically debated, these narratives reveal how cultures worldwide intuitively understood caves as biological time capsules long before germ theory existed. The ethical implications are profound. When Navajo guides refused to enter a newly discovered chamber in Arizona's Canyon de Chelly, citing tribal prohibitions against disturbing the Old One's breath, they spared researchers from what could have been a fatal mistake. Laser scans later revealed lethal concentrations of carbon dioxide pooled in the chamber's lower passages, an invisible danger the tribe's oral histories had encoded as the sleeping death wind. This incident sparked a paradigm shift in cave research protocols, with institutions like the National Speleological Society now requiring consultation with local indigenous groups before exploring significant new voids. What emerges is a dialogue between ancient intuition and modern methodology. The Yakut shamans of Siberia have long described certain permafrost caves as mirrors of the sky's memory, where past atmospheres are preserved like reflections in ice. Scientists studying these sites recently confirmed they contain layered air pockets spanning 12,000 years, a climate record that aligns with the shaman's cyclical conception of time. Similarly, when Amazonian Tucano people described caves where the forest soul breathes backward, researchers discovered these spaces act as carbon sinks, with plant-derived gases showing inverse seasonal patterns compared to surface air. This fusion of tradition and technology is yielding unexpected breakthroughs. In South Africa's cradle of humankind, archaeologists following San Bushman's star lore located a previously unknown cave system rich in ancient air pockets. The Bushmen's stories of the place where stars touch the earth referred to unusual mineral deposits that glow under ultraviolet light, the same deposits scientists now use to identify caves likely to contain well-preserved atmospheres. As we stand at this crossroads of knowledge systems, each new discovery reinforces a humbling truth. Sometimes the most advanced instruments merely confirm what careful observers discerned millennia ago. Imagine holding a vial of air from the last ice age in your classroom, not a simulation, but actual molecules exhaled by woolly mammoths and inhaled by early humans. Sealed cavern research is revolutionizing science education by turning abstract theories into tangible experiences. At the University of New Mexico, geology students don VR headsets to explore Lechuguilla Cave's deepest chambers, collecting virtual air samples that mirror real data from expeditions. They're not just memorizing gas ratios, they're tracking how methane levels spiked during prehistoric warming events, drawing direct parallels to today's climate graphs. This hands-on approach transforms statistics into stories, helping learners grasp complex systems through immersive interaction. The power lies in bridging scales, both time and size. Middle schoolers in Texas use classroom spectrometers to analyze ancient pollen grains from Carlsbad Cavern's air pockets, comparing them to local vegetation records. Suddenly, a lesson on photosynthesis becomes a detective story spanning 12,000 years, where students uncover how shifting CO2 levels altered entire ecosystems. Even younger children get involved. A Canadian elementary class built a model cave system with layered atmospheres, using baking soda, vinegar, and food coloring to visualize how gases stratify over centuries. These activities distill PhD-level research into foundational concepts without diluting their significance. Digital tools are erasing barriers entirely. The Paleo Air Project, a collaboration between Stanford and the Smithsonian, lets anyone download datasets from Romanian cave studies to create their own climate models. Meanwhile, the Cave Sim virtual lab, developed by MIT engineers, uses gaming mechanics to teach sampling protocols. Players earn points for avoiding contamination while extracting virtual ancient air. Such platforms don't just educate, they democratize access, allowing a teenager in Nairobi to study Ice Age atmospheres with the same tools as researchers in Vienna. The ripple effects extend beyond STEM. Art students at Chicago's SAIC recreate cave bacteria's bioluminescence in installations, while creative writing programs use cavern discoveries as prompts for speculative fiction. One striking example, after learning about Movile Cave's isolated ecosystem, high schoolers in Atlanta wrote from the perspective of its blind insects and exercised blending biology with empathy. Even ethics classes debate the dilemmas these sites pose, weighing scientific progress against preservation in ways that mirror real-world controversies over rainforests or coral reefs. What makes these educational initiatives so transformative is their authenticity. Unlike textbook diagrams, cavern data carries the weight of real discovery, the thrill of the unknown. When Arizona State University partnered with local cavers to share LiDAR scans from Karchner Caverns, students identified 3 potential new air pockets that professionals had missed. That eureka moment, when a freshman's observation contributes to actual science, is the kind of spark that ignites lifelong curiosity. As one teacher noted after her class analyzed sulfur isotopes from Cuva de Villa Lus, they're not just learning about science, they're living it, one ancient breath at a time. Preserving these underground time capsules requires a delicate balance, advancing science while leaving minimal footprints. The newest frontier in cave research isn't just about discovery, it's about restraint. Teams now deploy spider-like robots no larger than a human hand to navigate passages too fragile for human explorers. These mechanical scouts, equipped with microscalpels and nanotube filters, can collect gas samples through pores thinner than a human hair, leaving the surrounding rock untouched. In Spain's El Soplao cave, such probes recently extracted 300,000-year-old air from behind a calcite curtain without cracking its crystalline seal, a feat akin to performing keyhole surgery on a snowflake. Blockchain technology adds another layer of protection. Every measurement, from methane concentrations to humidity levels, gets encrypted and time-stamped in decentralized ledgers. This isn't just about data security. It creates an unbroken chain of custody for samples that may be reanalyzed centuries from now. When researchers in Oman's Majlis Al Jinn discovered anomalous helium isotopes in 2023, they could trace every handling step back through the blockchain, ruling out contamination with cryptographic certainty. Such systems prevent disputes over findings while ensuring future scientists know exactly how original samples were collected, crucial when studying materials older than human civilization. Legal protections are evolving too. The proposed Underground Heritage Act would extend UNESCO-style status to significant subterranean sites, categorizing them based on atmospheric uniqueness rather than just archaeological value. Drafted with input from indigenous groups and climate scientists, the treaty recognizes caves like Namibia's Dragon Breath Cave, home to Earth's oldest known isolated air, as non-renewable resources more precious than any mineral deposit. Violations could carry penalties similar to trafficking endangered species, reflecting how these chambers hold not just air but irreplaceable chapters of planetary history. The most radical shift may be philosophical. Where early speleologists prized collection, modern researchers emphasize documentation over disturbance. Advanced spectroscopy now allows virtual sampling, analyzing air chemistry through impermeable barriers using quantum tunneling effects. Italian teams recently mapped an entire Etruscan-era Caverns atmosphere with terahertz scanners, creating a digital twin so accurate it revealed seasonal gas variations from 2,000 years ago. This paradigm treats caves like museum exhibits under glass, studied intensely, touched minimally. These protocols aren't just about ethics, they're practical necessities. When Greenland's ice core repositories revealed gaps from mishandled samples in the 1970s, scientists lost crucial climate data forever. Cavern researchers aim to avoid similar regrets by treating every sealed chamber as if it might hold the next revolutionary discovery. After all, today's untouched cave could tomorrow answer questions we don't yet know to ask about pandemics, geoengineering, or even extraterrestrial life. Preserving these options requires recognizing that some doors, once opened, can never truly be closed again. The air trapped in sealed caverns might seem like a purely scientific curiosity, but its economic value extends far beyond research labs and academic papers. Consider agriculture farmers battling unpredictable weather patterns are now using data from ancient cave atmospheres to refine their planting strategies. In California's Central Valley, vintners consult paleoclimate records preserved in nearby caverns to anticipate drought cycles, adjusting irrigation systems based on 1,000-year-old rainfall patterns revealed in the isotopes of trapped air. Similarly, civil engineers designing flood barriers in Vietnam's Mekong Delta incorporate data from local caves that show how monsoon intensities have fluctuated over millennia, ensuring infrastructure can withstand both historical extremes and future projections. Pharmaceutical breakthroughs represent another unexpected windfall. The same extremophile microbes that thrive in toxic cave atmospheres are proving to be gold mines for new medicines. A bacteria strain discovered in Mexico's sulfuric Cuva de Villa produces a compound that obliterates antibiotic-resistant MRSA, a discovery now licensed to a biotech firm developing next-generation infection treatments. Meanwhile, enzymes from Movile caves' sulfur-eating organisms are being adapted to break down microplastics, offering potential solutions to one of our most persistent pollution problems. These innovations didn't come from targeted searches, but from fundamental research into how life persists in Earth's most isolated environments. Geotourism has turned once obscure caves into economic engines. Kentucky's Mammoth Cave National Park, where climate research happens alongside public tours, generates over $75 million annually for local communities. But the real innovation lies in how these sites fund their own conservation. Slovenia's Postojna cave uses ticket revenue to maintain sterile research zones where ancient air samples are collected, proving that public access and scientific integrity aren't mutually exclusive. In China's Zhangjiajie National Park, virtual reality tours of restricted caverns satisfy tourist curiosity while protecting fragile atmospheres, creating a sustainable model that's being replicated worldwide. The financial ripple effects even reach Wall Street. Insurance firms now factor cave-derived climate data into risk models, recognizing that prehistoric atmospheric shifts offer clues about modern vulnerability. A reinsurance giant recently adjusted its Caribbean hurricane coverage after analyzing methane spikes in Bahamian blue holes that revealed forgotten mega storms from 3,000 years ago. Similarly, mining companies use cave gas compositions to locate untapped mineral deposits, since certain atmospheric signatures correlate with underground ore formations. Perhaps most compelling are the jobs created at this intersection of science and industry. From the engineers designing cave-preserving tourist walkways to the lab technicians culturing cave microbes for pharmaceutical use, These opportunities demonstrate how curiosity-driven research can fuel entire sectors. As one economist noted while studying the impact of New Mexico's Carlsbad Cavern research, every dollar spent studying ancient air generates $7 in downstream value, not bad for something we can't even see. This economic alchemy transforms subterranean whispers into tangible prosperity, proving that protecting Earth's atmospheric archives isn't just about understanding the past, it's an investment in our collective future. Determining the age of ancient air trapped in caverns isn't as straightforward as reading a date stamped on a bottle. It's more like piecing together a fragmented manuscript where every scientist brings their own deciphering tools. Take the heated debate surrounding Brazil's Toca da Boa Vista caves, where two leading labs arrived at wildly different estimates for the same air pocket. One team, using Krypton 81 dating, claimed the atmosphere was isolated for over 400,000 years. Their rivals, employing carbon-14 analysis of trapped organic particles, argued it was no older than 50,000. The discrepancy, Krypton dating measures how long the air has been sealed, while carbon dating reveals when biological material entered the cave, a nuance that sparked years of methodological soul-searching in the field. Contamination remains the specter haunting every study. In 2018, a celebrated paper about million-year-old air in Siberian caves faced scrutiny when critics noticed the sampling drill had briefly overheated, potentially cooking modern gases into the ancient mix. The controversy led to a remarkable innovation, the triple lock protocol now used in sites like Namibia's Dragon Breath Cave. Here, researchers first laser drill a microscopic pilot hole, then flush it with inert argon to purge contaminants, and finally insert a cryogenic probe that freezes samples the instant they're extracted. Such rigorous standards emerged directly from past embarrassments, turning what could have been scientific dead ends into roads toward greater precision. The leak hypothesis stirs even fiercer debates. When a French team claimed to have found 200,000-year-old air in the Chauvet cave, skeptics pointed to calcite deposits showing hairline fractures too fine for standard detection. Their argument, these microfissures could allow slow gas exchange over millennia, making the air a palimpsest of different eras rather than a pristine snapshot. This challenge birthed new imaging techniques, micro-CT scanners that create 3D maps of rock porosity, and helium tracer tests that reveal seepage invisible to the naked eye. Ironically, the very uncertainty these tools address has become their greatest selling point, as funding agencies now prioritize projects that account for leakage risks in their designs. What makes these controversies so productive is how they expose science's self-correcting machinery. The infamous Pleistocene Skies paper of 2016, which claimed to reconstruct Ice Age wind patterns from Spanish cave air, was eventually retracted when an early career researcher noticed the team had overlooked seasonal humidity fluctuations. That correction didn't just improve one study, it revolutionized sampling calendars worldwide, with expeditions now timed to avoid periods when cave, breathing natural air currents could distort results. Similarly, disputes over isotopic fractionation in Greek caves led to the development of correction algorithms now baked into every mass spectrometer's software. The biggest revelation from these clashes isn't about caves at all, it's about how science evolves. Each challenge forces researchers to articulate their assumptions, defend their methods, and ultimately build sturdier knowledge. When Norwegian scientists questioned whether Antarctic subglacial caves contained truly ancient air or just recirculated modern atmosphere, the resulting experiments didn't just settle the debate, they spawned an entirely new subfield studying how ice sheets filter gases. This iterative process, messy as it may seem, ensures that every claim about Earth's atmospheric past earns its validity through rigorous trial by combat. After all, if caverns teach us anything, it's that preservation isn't about stasis, it's about dynamic systems finding equilibrium amid constant change. The life of a cavern researcher reads like an adventure novel, one where the stakes include both scientific revelation and survival. Take Dr. Emily Harrington's harrowing experience in New Mexico's Lechuguilla cave, where a routine survey turned into a 6-hour ordeal after a rockfall sealed her team's exit. As oxygen levels dropped and headlamps flickered, they followed a trickle of air through a crack no wider than a dinner plate, emerging into a pristine chamber where the air tasted, as she described it, like inhaling the Pleistocene. The pocket they discovered contained methane levels matching ice core records from 40,000 years ago, but what stuck with her wasn't the data. It was the silence, not the absence of sound, she clarified, but the presence of time itself. Then there's the chilling account from Romanian microbiologist Dr. Radu Popa in Movile cave, dangling from a rope above a sulfuric lake. His gas monitor screamed warnings as hydrogen sulfide concentrations hit lethal levels. What should have been a retreat became a discovery when his trembling flashlight revealed microbial filaments growing across the ceiling, organisms thriving where science insisted nothing could. They were dripping acid strong enough to burn my glove, he recalled. Yet there they were, rewriting biology's rulebook by the glow of a dying headlamp. That moment of terror birthed a decade of research into chemosynthetic life, with implications stretching to Mars' subsurface voids. Not all stories pulse with danger. Sometimes revelation comes softly, like when Australian geochemist Dr. Lin Nguyen noticed her breath forming unusual patterns in her headlamp beam within Vietnam's Hang Son Doong. The swirling vortices led her to an air current. No one had documented a natural ventilation system preserving distinct atmospheric layers dating back to the last glacial maximum. It was like finding a library where each shelf held a different era's air. She mused. Her subsequent papers on microclimate stratification fundamentally changed how researchers model cave preservation globally. The emotional toll resonates as deeply as the physical risks. Dr. Carlos Munoz Reyes still dreams about the echo that haunted his team in Chile's Patagonian marble caves, a sound wave reflection so precise it recreated the acoustics of a long collapsed chamber. For 3 seconds, we heard what the cave sounded like when Paleolithic humans first entered it, he said. That fleeting auditory ghost now drives his work, reconstructing ancient soundscapes from air density data, blending archaeology with atmospheric science in ways no one anticipated. What unites these researchers isn't just courage, but a shared moment of transcendence, an instant where science flips into something more personal. For Dr. Aisha Diallo, it came when sampling Mali's Dogon caves, where local elders insisted the chambers held the breath of ancestors. Her mass spectrometer later detected unique pollen varieties matching oral histories of a vanished forest, proving tradition and data could converse across centuries. We think we're documenting the past, she reflected, but really we're learning how to listen. These aren't just fieldwork anecdotes, they're reminders that every dataset has human fingerprints. When a researcher's boot slips on wet calcite or their laughter bounces off million-year-old stalactites, they're not just collecting samples, they're adding another verse to an epic poem about curiosity. The true signature of their work isn't just in published papers, but in the mud-stained notebooks, the inside jokes about bat guano, and the way they all eventually describe their caves not as sites, but as collaborators in Earth's greatest story. From the moment we first breached these subterranean vaults, sealed caverns have rewritten our understanding of Earth's story. They're not merely geological formations, They're living libraries where every gasp of trapped air, every mineral-encrusted microbe, and every layered dust particle forms a chapter in our planet's autobiography. Think about what we've uncovered: air samples showing how mammoths breathed, microbes surviving in suspended animation for millennia, and climate records proving that today's atmospheric changes are unprecedented in their speed and scale. These discoveries didn't just add to existing knowledge, they created entirely new fields of study, from paleobarometry to chemosynthetic ecosystem modeling. What makes these hidden chambers so extraordinary is their duality. They're both time capsules and crystal balls, the same ancient air revealing how forests responded to prehistoric warming also helps predict how modern ecosystems might cope with climate change. Those extremophile bacteria thriving in toxic cave atmospheres, they're not just scientific curiosities, they're teaching us how life could persist on Mars or Europa. Even the controversies surrounding cavern research have value, pushing scientists to develop more precise tools and ethical frameworks that benefit disciplines far beyond speleology. Yet for all our technological advances, perhaps the greatest lesson from sealed caverns is humility. These environments remind us how recently we've arrived on Earth's timeline, how the air in New Mexico's Lechuguilla cave was already ancient when humans first painted mammoths on cave walls in France. They show the consequences of planetary-scale changes, but also the resilience of life in the most improbable places. Most importantly, they prove that some of science's greatest breakthroughs come not from dominating nature, but from collaborating with it using non-invasive techniques to listen rather than disrupt, to preserve rather than plunder. The exploration continues, with each generation of researchers building on the last. Quantum sensors may soon let us analyze cave atmospheres through solid rock, while AI helps reconstruct lost climates from fragmentary data. But the fundamental wonder remains unchanged. Beneath our feet lie archives more comprehensive than any human record, waiting to reveal their secrets. Whether you're a scientist, an adventurer, or simply someone who gazes at mountains and wonders what lies within, these subterranean wonders invite us all to keep questioning, discovering, and respecting the delicate balance of our planet. The next chapter in this underground saga is yours to write, through curiosity, conversation, and a shared commitment to preserving these irreplaceable portals to the past. What we learn there might just help us navigate the